Hello and welcome to Lecture 2 of the Vectors unit. We've already been talking about displacements and positions, and displacements are a difference or a subtraction of positions, and positions are vectors. So we need to know how to understand subtracting vectors. We're often going to have to add and subtract vectors. In fact, we've already done it to get displacements. We just haven't looked at it like vector addition. So, in grade 1 or even earlier, you learned to do scalar addition. 3 apples plus 4 apples is 7 apples, last time I checked. But vector addition doesn't work that way. 3 meters east plus 4 meters north isn't 7 meters in any direction. So let's see how this works. And the thing to realize is that plus just means and. And so if we think in terms of displacement vectors, we can see how this works. If you start at some location, you walk 3 meters east. And, notice the and then you walk 4 meters north. What is your total displacement vector? Well, it certainly isn't 7 meters long. Your total displacement vector is going to be a vector that points from where you started to where you finished up. And so there it is, and a little bit of trigonometry will show you that it's 5 meters, roughly 53 degrees north of east. This triangle here, where we've taken the two vectors we're adding and put them head to tail, is really the definition of vector addition. And you see, it doesn't look much like scalar addition, and it doesn't give an answer anything like what scalar addition does. So this is what we say this is what we mean when we say C is A plus B, where they're vectors, written either way. The two vectors I just added happened to be at right angles from each other, and I've often seen students think that that's the only time this works, but in fact it works for any vectors. So let's look at these vectors a, b, and c, and let me find some vector d, which is a plus b. So I'm going to just take a and I'm going to redraw it over here. So here is a, 5, that's a. Now I'm going to redraw B, and notice I'm going to put them head to tail, because that's what we just saw. That's how you do vector addition. You take the two vectors and you put them head to tail. And I'll just stress, what I'm doing here is called graphical vector addition. And by graphical, again, I don't mean graphing. I mean graphical has to do with drawing. So there we go. There is D, found from A and B. And the thing to notice is the last step. We started over here, drawing A, and we finished up over here, drawing B. And so D points from where we started to where we ended up. So now I'll just quickly do E, and just remind you that you can always just slide vectors around. So I'm going to do just that, partly to speed things up here. So there's A, and now I'm going to take C, and I'm going to put it head to tail with A. And now I'll draw in E like so. So there is E. An important special case is when the vectors are parallel or anti-parallel. So let's just do A plus B with these new vectors. So here's A. Here's A. And now I'll redraw B head to tail with it, right? So B winds up right here. And now remember, we started right here, and we ended right here, so we have to draw our result in starting there and ending there. And just because it's very unclear otherwise, instead of putting it right on top of them, I'll just displace it a little bit to the side so that it's visible. So there is D. Now let's look at when they point in opposite directions. So again, I'm going to draw B like so. So here's B. Now if I try and draw C right on top of it, it's going to be difficult. So I'll draw C just a little bit displaced, like so. Okay, so there's B, there's C, and now remember that we started here and we ended here, so I'm going to draw the result, E, from where we started to where we finished, and it's just that little vector right there. With what we've just looked at, we can now see what it means to multiply a vector by a scalar. Because think about this. If I wanted to know what 2 times A was, well, I just have to add A plus A. That's 2 times A. So let's do that. I'm just going to grab A, carry it down here, and I'll grab another copy of it and carry it down, and there we go. There's 2A. So notice that we've just wound up with a vector in the same direction as A and twice as long. So similarly, 3A would just be the same thing. It would be a vector a vector in that direction, but 3 times as long as A. Okay, or 2.5A, and so on. So what if we multiply by a negative? Think about what negative A looks like. Well, what we know about negative A is that A plus negative A must be 0. I mean, that's what we mean by taking the negative of something. So if I grab A, and now I'm going to say that negative A is the thing that points back in the opposite direction. Oops. Negative A would point back in the opposite direction so that wherever we started, that's where we finish up. So there's negative A. And so now you see what the negative means. Just flip the direction. Right? So if I have some arbitrary vector, here's, you know, some vector, I don't know, Q. The negative Q is just, oops, negative Q is just this vector. Now I just want to point something out. What we're doing here is multiplying vectors by scalars, right? This is a vector. But this 2 here has no direction associated with it. That's a scalar. Okay, we haven't looked at all at how you multiply vectors by other vectors. There are actually several ways to multiply vectors by other vectors, or maybe what I should say is there are several types of multiplication for vectors and vectors, but we won't see any of them in this course. Now that we know how to multiply a vector by a negative scalar, we know how to do vector subtraction. Because think about C, that is some a minus b. We can rewrite that as a plus negative b. So what we need to do to subtract them is first take b and flip it around so that we get negative b. So there's negative b. And now let's add them. So I'll redraw a over here. There's a. And now I'll redraw negative b, which goes like this. And let me just label them to make things clear. So this is a, and this is not b, this is negative b. And so now the vector we get when we add them, c, we go from where we started drawing a to where we finished drawing b. And so there is c. And let's just see that with parallel vectors. So again, I'll define an f that is d minus e, and so I'll start by redrawing d. So there's d. I'm going to redraw e over here flipped around. So that is negative e. And so now I'll stick it over here. We have to go head to tail. So I put the tail of negative e where the head of e is, or the head of d. So let me just label those. This is d, and this is negative e. And so f, which is d minus e, goes from where we started to where we finished up. Oops, let me do that a little better. There. We've seen a lot new in the last 2 lectures, so let's just take a moment to summarize. Vectors have a size, we call it magnitude, and they have a direction. And they're independent of how you define your coordinate axes. And since they're defined by their magnitude and direction, you can slide them around as long as you don't change their size or which way they point. You can slide them around and they remain the same vectors. To add 2 vectors, you stick them head to tail, and you draw a new vector from the tail of the first one to the head of the second one, and that's the sum. You multiply vectors by scalars just by stretching them or contracting them for scalars less than 1. And if the scalar is negative, then you flip the direction of the vector. And that gives you your way of doing vector subtraction. You just take the vector being subtracted, so here I've taken b, and you flip its direction, and now you add them.